In this video, I'm going to look at a number of organic chemistry questions that have appeared in previous GCSE papers. The first question then is asking us to name A, B, C and D. So let's look at A. There are no carbon-carbon double bonds, so this is a saturated compound. It's made up of carbon and hydrogen. That means it's an alkane. And if there are two carbons, it's ethane. B, now there is a carbon-carbon double bond. This is unsaturated. It's again just made up of carbons and hydrogens. This time it's an alkene. 3 carbons, so it's propane. On to C. Again, there is a carbon-carbon double bond. This is unsaturated. So this alkene is ethane. Finally, D. 4 carbons, so it's bute. It only contains carbon-carbon single bonds, so it's saturated. Therefore, this is an alkane. This would be called butane. Next part, write the molecular formula for substance D. You can see D over here. There are 4 carbons, so it's going to be C4, and then you just count the number of hydrogens, H10. Notice that carbon has 4 bonds. Doesn't matter if it's an alkane or whatever other organic chemical it may happen to be. Carbon must always have 4 bonds around it. Which one has the empirical formula of CH3? This is the simplest whole number ratio of atoms in a molecule. Well, if you take a look at A, it has the molecular formula, so that's the actual number of atoms in a molecule. It's C2H6. That can be simplified. We can divide by 2. So CH3 is the empirical formula of A. Then write a balanced simple equation for the complete combustion of B. B is C3H6. Going to react it with oxygen, and it's complete combustion. So that will produce carbon dioxide and water. Start with the carbons. There are 3 carbons on the left. We need 3 on the right. Just put a 3 there. Then do the hydrogens. There are 6 on the left. So over here, you need to put a 3 in front of that. And then finally finish with the oxygens. So 3 2s are 6, plus 3 is 9. So over here, to make this 9, we can simply add 4.5. Now you can do a multiple here. So what you could also do is multiply this whole thing by 2. So it would be 2 and 9, 6 and 6. Part 5, homologous series. So these are this is a series of compounds, the same general formula, and just notice here, don't say substances. Okay, that's not right. It has to be compounds or molecules. So the same general formula, differ by a CH2 group or CH2 unit. They will have similar chemical properties, and don't say the same chemical properties that are not. There will be a variation. And then the final thing you could say is there's a gradation in physical properties. So 3 marks, 3 of those things would be fine. On to B part 1. What is meant by the term hydrocarbon? Well, it's a standard definition. This is made up of 2 words, hydrogen and carbon. So this is a compound or molecule, again we'll say substance, that is made up of hydrogen and carbon only. Part 2. What type of polymerization is used to form polythene? So obviously this is polythene. And alkenes undergo addition reactions. Now just be careful here that you don't say additional. I'll just put that in because additional is wrong. Part 3, what do you understand by the term polymer? So something like a long chain molecule. So long chain and molecule are key there. And it's made up of smaller molecules, or you could say made up of monomers. Part 4, name the monomer from which polythene is formed. Well, this is actually polyethene. And if we go back up to here, the monomers used to make the polymers are always based on 2 carbons. So if we take here and here, then the monomer is going to be the 2 carbons, but now with a double bond. And then hydrogens are around it. So you can see the bonds that were on either side of the carbon, so that's here and here, have now gone. And then the double bond is in here. Every carbon must have 4 bonds. So this here is ethene. So this is polythene or polyethene. This is ethene. Part 5, a structural equation to show the polymerization of vinyl chloride or chloroethene. Chloroethene is the modern name for vinyl chloride. Now, all of these addition polymers are based on ethene, if you think of it that way. So ethene has 2 carbons, it's carbon double bond carbon, and one of the hydrogens is replaced with a chlorine. So that's vinyl chloride or chloroethene. And we have n number of those because a polymer can be made up of thousands of these molecules, these monomers. And then when they join, the double bond breaks, and then we show that the molecule continues either side. I'm just going to then draw the atoms around this. And finally, I have to use brackets. So we're going to put brackets, and we normally use square brackets, ensuring that the brackets go through the bonds. I'll just do the other side as well. And because I've used n number of monomers, that's going to form n number of those molecules in the polymer. Next question then, A part 1, is explain why this molecule is a hydrocarbon. We've asked that, or that has been asked before. That's just a molecule or compound that contains carbon and hydrogen only. Part 2, identify the functional group. Well, you can see a functional group here, here and here. Carbon-carbon double bond. That's it. Okay, then on to this next question, B. This is linalool, and part 1, on the structure, draw a circle around the alcohol functional group. Now, the functional group in an alcohol is hydroxyl, which is OH. So I can see it here, and I'm just going to draw it around that. And make sure that you don't do that, because carbon is not the functional group, it's just the OH. Next question is completing this question, and it is complete combustion. Well, again, when any of these organic chemicals burn in air, it just forms carbon dioxide and water. So that's the first thing I'm going to put in. So CO2 plus H2O. I'm going to start with the carbons. 10 on the left. I need 10 on the right. Do the hydrogens. 17 plus the 1's 18. So I can 9 2's will make 18. Then finish with the oxygens. So here we've got 20 plus 9 is 29. Now you need to be careful when you're doing these balanced equations for the alcohols, because it is not just O2. Remember, there's an O already here. So what I would do is, if I go back to the right hand side, there 20 plus 9, that's 29. On the left hand side, I already have 1. So that means I now need 28. So I can just simply put a 14 in front of that, and then that all adds up to 29. Part 3, if we warm this with acidified potassium dichromate, the colour change is orange to green, because this alcohol will get oxidized to the carboxylic acid. See part 1, the general formula for alcohols. CN, H2N plus 1, OH. And then part 2 is asking us to draw the structural formula for ethanol. So we're going to show all of the bonds here. or at least all of the bonds around this part, you can just write OH. If the question had clearly stated to show all of the bonds, then you would have shown the bond between the O and the H. Now, if you've done the O down here, which is perfectly fine, or you could have put the OH on this side, but the carbon must be bonded to the O. So again, if I just do it this way, just to make you understand what I mean, it must be that. Do not do this, okay? That'll cost you a mark. And then part 3, we have to give the molecular formula for ethene. Well, the eth tells me that there are 2 carbons, and then there are going to be 4 hydrogens around it. The ene part tells me it's an alkene. Now, it may be easier to draw the structure formula first, if you can't remember that. So, eth, I know there's a double bond, and then I've got to finish it off. So, the carbons have 4 bonds. And all of the alkenes that you study at GCSE are gases, same as the alkanes. D part 1, draw the structure formula for ethanoic acid. Okay, there. F part tells me there are 2 carbons. Oic acid is a carboxylic acid, so it is C double bond O, OH. So this is the functional group for carboxylic acid, COOH. And then I need to remember to complete this with hydrogens. Again, ensuring that all of the carbon has 4 bonds. Part 2, 2 observations that you would make when magnesium reacts with ethanoic acid. Well, this is just like magnesium reacting with any acid. So you're going to have things like fizzing or bubbles. The magnesium disappears. Now remember, don't say dissolves there, that's wrong. Heat's released. And the final thing you could say here is that a colourless solution is formed. But there are 2 marks, you only need 2 things. On to the next bit. A balanced assembly equation for magnesium reacting with ethanoic acid. Okay, well, magnesium is Mg, ethanoic is CH3COOH, and that forms magnesium ethanoate. Now, there are 2 ways you can do this. I'm going to do it this way first of all. So that's ethanoate, because you get magnesium ethanoate formed, and this whole thing is a valency of 1. Magnesium is a valency of 2. So that's magnesium ethanoate. And this here is a metal plus an acid, gives an salt plus hydrogen. And to balance it, well, you can see there are 2 ethanoates here. So we're going to need 2 over here. Now you can write that a slightly different way. You could do Mg before the ethanoate. Okay, so that's fine. Next part then, we have to fill in this table. So the general formula for alkanes is CnH2n plus 2. And for the alkenes, the molecular formula of the compound with 3 carbons is going to be C3H6. Part 3, name the alkane, that is C3H8. Well, it's going to be based on prop. That means 3. And because it's an alkane, it's going to end in ANE. So it's propane. What is meant by the term combustion? Again, a definition you need to learn. So this is when a fuel reacts with oxygen, forming oxides and releasing heat. And part 2, write a balanced equation for the complete combustion of methane. So CH4, these seem to be popular types of questions, plus O2. Again, it's complete combustion, so we're going to get carbon dioxide and water. Remember, incomplete combustion means there'll be carbon monoxide formed instead. So do the carbons first, So there's one here, so I don't need to do anything here. 4 hydrogens, need to put a 2 there, and then finally finish with the oxygens, a 2, and 2 is 4, so we just need to put a 2 there. Alkenes contain the C double bond C functional group. What do we mean by the term functional group? Well, it's just the reactive part of the molecule. For the alcohols, it's going to be the hydroxyl group. For carboxylic acids, it'll be the carboxyl group. That one, or we could do it that way instead. Okay, the chemical test then to show the presence of this C double bond C, which is present in alkenes. Well, we're going to add bromine water, and we'd normally shake that. So I'm just going to put in shake. And this bromine water is orange, or yellow orange, or orange brown. And if there's a double carbon-carbon double bond present, it'll go to colourless. D, this question was asked before. Polyvinyl chloride. So vinyl chloride is the monomer, or remember the modern name is chloroethene. 2 carbons, replace one of the hydrogens, that's an ethene, with a chlorine. And again, we put an N in front of it to represent just any number. And then when lots of these monomers join, the double bond breaks. Bonds form either side, and then I'm just going to complete it with the hydrogens and the chlorine. Now I put brackets through the bonds and put the N outside. One reason why PVC is used to make window frames in preference to wood, things like it's more durable or doesn't rot, needs less maintenance. I wouldn't say something like it's cheaper, things like that, because obviously wooden windows could be expensive as well. On to this question. Compound A, well, it is an alcohol because it's got this hydroxyl group, and we don't say it's an alcohol group, it's a hydroxyl group. There's 1 carbon, therefore this is going to be methanol. The functional group in B, well, it's got the C double bond to OH, that is carboxyl. Now it doesn't say to give the name here, so you could also just say COOH. Compound C is a hydrocarbon. Again, I'm not going to write that in, we've done it before. That's a compound or molecule containing hydrogen and carbon only. And part 4, which compound reacts with sodium carbonate? Well, sodium carbonate, any carbonate, reacts with acids, and B is the only acid here. It's ethanoic acid. Okay, on to this question about fermentation. To describe the production of ethanol by fermentation. Now remember, ethanol can be made industrially by reacting ethene with steam. I'm just going to show you it. This is not part of the question, but you do have to know how this is made using steam. So obviously the H2O is not liquid water, that's steam. That would be a gas, and then that goes to give your ethanol. Again, there would be hydrogens around that. So in this answer, we must include the names of the starting materials. Right, so we're going to start off with a sugar solution, or you could say sugar dissolved in water, or a glucose solution. Going to require yeast, and the absence of air, or you could say anaerobic conditions. It needs to be warm, not hot. Okay, something like 30 degrees C or thereabouts. And let's see what else do we need. So we've got the names, conditions required, and then the names of any other products formed apart from ethanol. Well, the other product is carbon dioxide. Part B. What is the general formula of the alkanes? Again, that's just going to be CnH2n plus 2. Hydrocarbon, again, you can see it's a popular question. Number 3, or part 3, the complete combustion of octane. Well, you're given the formula for octane up here. So it's going to be C8H18. Again, it's the complete combustion. So it's going to be plus O2. That tells us it's going to be carbon dioxide and water that are formed. So start off again with the carbons. 8, we need 8 here. There are 18 hydrogens, so we need 9 here to make that up to 18. Finally finish off with the oxygens. 16 plus 9 is 25. So over here we need 25. We can just do that again. If you don't like those halves, you can multiply the whole equation by 2. On to C. Just move this up a bit. A is converted to B by reaction 1 and B is converted into C by reaction 2. Okay, so name A, B and C. Well, A is an alkene. It's got a carbon-carbon double bond. B, again, is named after eth. And it's got this OH group, which tells me it's an alcohol. So it's ethanol. And then finally C, that's a carboxylic acid. And because it's got 2 carbons, it's ethanoic acid. Part 2, name the substance which reacts with A in reaction 1 to form B. Well, I did that just a few moments ago. This is an alkene, this is an alcohol, and industrially, alkenes can be converted into alcohols by a reaction with steam. Don't say water, it must be steam. Part 3, reaction 2 may be carried out using acidified potassium dichromate. What's the colour change? Well, potassium dichromate is orange. And when it oxidizes an alcohol to the carboxylic acid, it turns green. Okay, what substance would decolorize bromine? Well, that was the alkene, the carbon-carbon double bond. That was A. So I'm just going to put that in. Okay, homologous series. Again, I've done that before. So I'll just read those out. Those are compounds or molecules with the same general formula, similar chemical properties. Remember, don't say the same. There's a gradation in physical properties and they differ by a CH2 group. On to B part 1. What is the functional group in cyclohexene? Well, you can see it here, and you can also identify it by the name. It ends in ENE. So that means this is an alkene. And alkenes have this C double bond C. Or you could write it that as a word. You could just write out carbon-carbon double bond, etc. Hydrocarbon, again, compounds or molecules that contain hydrogen and carbon only. When cyclohexene is burnt in a limited, okay, this one's different now to before. It's a limited supply of oxygen. So this time we get carbon monoxide instead of carbon dioxide and water. What's the empirical formula of cyclohexene? You can see it over to the right. So again, at the minute, the molecular formula, which is the total number of atoms in one molecule, is going to be C6. You just count those up. H10. Now, the 6 and the 10 can be divided by 2, and so that will give us an empirical formula of C3H5. C part 1, what's the functional group of cyclohexanol? Well, you can see it's this OH group. So you can just simply do OH, or you can do hydroxyl. Don't say alcohol, that's the name of the compound. Balanced symbol equation. Okay, so it's going to be C6 H11O. H is complete combustion. So it'll give carbon dioxide and water. Again, as before, do the carbon. So 6 on the left, 6 on the right. 11 one's 12. So I need 6 there. And then finally finish with the oxygens. 12, 18. So I need 18 here. Now remember, there's already 1. So we need 18. So if we discount this 1, that brings us down to 17. So this here needs to equal 17. Just going to be 8.5. Again, you can have multiples there if you prefer. Part 3. Given practical details, describe chemical tests you would use to identify cyclohexene and cyclohexanol. Well, the cyclohexene has a carbon-carbon double bond, and the cyclohexanol has this OH group. So we have to give the names of the chemicals used to carry out the tests. Okay, so let's identify the C-double-bond-C. Just simply use bromine water. And again, you can say that you shake that, and it's orange or it can be brown. It just depends on the concentration of it. So I'm going to say it's orange, and it'll go to colourless. Now that's with cyclohexene. It'll obviously stay orange in the cyclohexanol. But the test we can do to identify cyclohexanol is to add acidified potassium dichromate, and this has to be warmed. And the colour change here would be orange to green. And as I said, that is with cyclohexanol. On to D, the molecular formula for ethanoic acid, CH3COOH. You could do CH4O2 as well, but it's typically written like that. The structure of formula we've had before. Why is ethanoic acid a weak acid? And this is true for all carboxylic acids. That is because they only partially ionize in water or in solution. Part 4. A Boltzmann equation for the reaction of sodium carbonate with ethanoic acid. Okay, now sodium carbonate is Na2CO3. The ethanoic acid is that. And this is just an acid plus a carbonate given a salt. So again, it's this hydrogen of the acid that reacts, so it gets lost. And then the CH3COO minus, so this has a valency of 1, as does the sodium. Again, you can put this the other way around, so you could have the Na on this part. But it's typically written like that. I'm going to get water and carbon dioxide. Now it needs to be balanced. So a 2 needs to go in front of that. And I think that's it, balanced. 2 observations when a carbonate reacts with the ethanoic acid. Again, this is just like with any acid. There's going to be fizzing or bubbles or gas produced. The carbonate will disappear. You could say a colourless solution formed. Sometimes heat's released as well, and that has been allowed in the past, but it's not always given a mark. So I would try to remember these 3 here rather than just say heat released. Okay, next question, homologous series. Again, I've done that before, so I'm just going to move on to part 2, which is actually also similar to one we've done before. The molecular formula for ethene is made up of 2 carbons, and it's an alkene, C2H4, and then C3H6. Again, I can tell that this is an alkene, CnH2n is the general formula. and it's propane. It's a gas. Ethene, propane, butane, butanone, and butene, those are all gases. The functional group of alkenes, C double bond C. Okay, on to this question then. Draw the structure forming for ethanoic acid. Again, that has been done before, but I'll just draw it in here. And always ensure there are 4 bonds around the carbons. I keep going on about this, but people often forget about it. What is meant by the term polymer? Again, this has to be something like a long chain is formed from small molecules, or something along those lines. Okay, on to then this, the structure of PTFE. What's the monomer from which PTFE is formed? Again, it's always based on ethene. Remember, you've got to pick out 2 carbons. So I'm just going to pick out these 2. And that's the basic structure of it. And the monomer always has a double bond between the carbons. So carbon, carbon double bond. And then just finish it off by using the atoms that are here. Well, these are all fluorines, so I'm just going to put in then fluorines around that. You don't include bonds here, because if you now put bonds there, this carbon and this carbon would have 5 bonds around it, which it cannot have. Malic acid, which is in cider, state the functional groups in malic acid. See here and here. So you can just do COOH and OH. But it doesn't say to name or write the formula. So either is fine. Or if you want to write the names, then you could say carboxyl and hydroxyl. The empirical formula. So again, this is the simplest whole number ratio. So what I'll do first is just work out the number of carbons, hydrogens, and oxygens present. Right, let's do the carbons first. They've got 1, 2, 3, 4. Hydrogens, 1, 2, 3, 4, 5, 6. And then finally the oxygens, 1, 2, 3, 4, 5. So now you have to think, well, can I simplify this? Well, no, I can't. I can't simplify it to whole numbers. So in this case, the molecular formula is also the empirical formula. Part 3. Sodium carbonate is added to malic acid. Again, this is like a previous question. This is like a carbonate with an acid. Doesn't matter if it's malic, ethanoic, propanoic, or even hydrochloric. It'll still produce the same. The reactions will be very, very similar. So we're going to get things like fizzing, the carbonate disappears, colourless solution formed. And a weak acid is one that partially ionizes in solution or in water. Okay, for this one here, I'm just going to go on to B. Draw the structure of but-1-ene. So the but part tells me that there are 4 carbons. 1, 2, 3, 4. The 1 tells me that the double bond is present and it's attached to carbon number 1. Now it doesn't matter if I do it in this end or this end. So I'm going to put it here. And then I just finish this with hydrogens because alkenes, like alkanes, are hydrocarbons. So 2 hydrogens are needed here. This carbon has already got 3 bonds. It just needs 1 more. I'm going to put it there. It doesn't matter if you can put it below it. That's also fine. And then hydrogens go around the others. Compare that to but-2-ene. So again, I need 4 carbons, but this time the double bond starts on carbon number 2. Now I finish it with hydrogens. 1, 2, 3, 4. 1, 2, 3, 4. There's butene. This question requires us to write a balanced assembly equation for the complete combustion of but-1-ene. So but-1-ene is C4H8 reacting with oxygen, again forming carbon dioxide and water because it's complete combustion. So 4, and then we need 4 there. 8 hydrogens, need a 4 there. So 4 2s are 8, plus 4 is 12, and you put a 6. See part 1. Okay, this is about cracking. Now, cracking is where a long chain molecule is broken into smaller alkane molecules plus an alkene. So I'll write the formula C7H16. This is my long chain molecule, and it's going to crack or break up into propene. And it is C3H6. Now, both sides of the equation have to balance. So there's 7 carbons on the left. We need a total of 7 on the right. We've already got 3. So that's going to be C4. H, again, the hydrogens have to add up to 16 on the left, or the same as on the left. We've already got 6. That means this must be 10. And part 2, name the other product forms. That's this one. That's going to be an alkane. When a molecule is cracked, you'll get an alkane and an alkene. So this alkane is based on 4 carbons. Therefore, it's butane. Suggest why high temperatures are required for cracking. Well, this molecule, I'm not going to obviously draw it all, but it contains lots of these. These are covalent bonds and they're strong, and so we require a lot of energy to break. D, state the type of polymerization which alkenes undergo. That's addition. Remember, don't say additional. That's wrong. Okay, so that would be wrong. It is just addition. Part 2, name the alkene from which this polymer is formed. Well, we've got 2 carbons and this chlorine, so that's going to be chloroethene. Or you can use the old name, which is vinyl chloride. Part 3, write an equation for the polymerization of ethene. So I'll draw my ethene molecule with an N in front of it. I did one like this earlier with chloroethene, but you can see it's the same type of equation. And then that goes to give my polymer. So the double bond breaks, and then bonds are on either side of the carbons. Draw brackets, which are usually square brackets, although just ordinary rounded brackets are okay, through the bonds, and then put an N outside. Part E, identify the functional group in alkene. So that's the C double bond C. And then write a balanced assembly equation when it's tested this way. Right, so I'm going to start off by saying it's a test for the carbon-carbon double bond, or that's the functional group that are present in alkenes. Again, you could just write that out as carbon-carbon double bond. Bromine water is used to identify this functional group, and it changes from orange, or you could say yellow or brown, to colourless. And then the final part here, we have to write an equation for the reaction which occurs when bromine water is added. So ethene is C2H4, and alkenes undergo addition reactions. So if we're reacting this with bromine, which is Br2, all we simply need to do is add the 2 molecules together. So it's going to be C2H4 Br2. Right, write the molecular formula of B. Okay, we just count up all the carbons. So 1, 2, 3, 4, 5. So it's going to be C5. And then the hydrogens, is 12. And name the homologous series to which it belongs. Well, these are all carbon-carbon single bonds. So this is an alkane. And that's all you have to write. Which of the organic compounds are hydrocarbons? So that's anything that's just carbon and hydrogen only. So it's obviously not A because there's oxygen. So B is a hydrocarbon. C is also a hydrocarbon, as is D. Not E, there's an oxygen there, and it's not F. Again, they're oxygens. Part 3, which two organic compounds have the same molecular formula? Well, that is A and E. The only thing that has changed between these two is that this OH group has moved here and the H has moved there. This is propan 1-ol and this is propan 2-ol. Part 4, a reagent which could be used to convert A into F. So this is an alcohol. If I show here the OH group, the hydroxyl group. This compound is alcohol and F is a carboxylic acid. So to go from an alcohol to a carboxylic acid, you need acidified potassium dichromate. And the type of reaction is oxidation. You can see here, even though we're adding in another oxygen. So, oxidation. Then on to part 5, name compounds E and F. So I mentioned this a few moments ago. This is propan, don't put in the E, hyphen 2 hyphen ol. Okay, so that's the way you need to write it. And then F is a carboxylic acid. There are 3 carbons, so it's based on prop, and then it's going to be propanoic acid. The complete combustion of C, or C4H8, again, complete combustion, so it's carbon dioxide and water. 4 carbons, so 4 CO2s, 8 hydrogens, 4 waters, and then we've got 4 2s are 8, 4 is 12, you put a 6 there. Part 7, draw the structure formula of another organic compound which has the same molecular formula as C and name the compound. So this is but2-ene. So what we can simply do is move the double bond here, or you can move it to here, and that will turn it into but1-ene. And both of those will have the same formula. So if I draw 4 carbons, and I'm just going to put the double bond here, then ensure that all of the carbons have 4 bonds, and I do that by surrounding them with hydrogens. And that's it. So the name of this is but2-ene. Next question. So here are some reactions of organic compound D. And for part 1, we have to name substance X. So that's here. So what you've got to think of here is what do we start with and what do we finish with. So we're starting off with an alkene. So this is an alkene. And this is an alcohol. And the way we can go from an alkene, like ethene, to an alcohol, like ethanol, is by using steam. Now, not water. Okay, it must be steam. What's observed when D reacts with bromine water? Well, bromine water decolorizes here. So it goes from orange, or you could say brown or yellow, to colourless. Name the type of reaction occurring in reaction Y. We're going from an alkene to this. Now this here is a polymer. This here shows you the repeating unit. So this here is addition polymerization. That's why there are 2 marks. One for addition. Again, remember, do not say additional. And then the second mark for polymerization. Part 4 in the box. Draw the structure formula for the reaction of D with hydrogen. Well, any time you react an alkene with hydrogen, you just add on the hydrogens to it and the double bond gets removed. So it goes from unsaturated to saturated. So still 2 carbons. There are the original 2 hydrogens, if you like, and then you just add on the hydrogens. But notice the double bond's gone, because if you keep the double bond, then the carbons will have too many bonds. So you turn the alkene into the alkane. Okay, on we go. Homologous series, that's been done before, so I'm going to skip that out. The functional group of the alkenes is C double bond C. Of the alcohols, it's OH, or you can do that, and then the carboxylic acid COOH. Part C, suggest why alkanes are less reactive than alkenes. Well, alkanes don't actually have a functional group. Okay, part D, draw the structure formula of ethanol and propanols. Both these are alcohols. Ethanol, 2 carbons, and then you put an OH in. I'm putting it here, but you could put it here or here. Make sure the bond is going to the O. And then just surround this with hydrogens. So again, just be careful here that you don't do this type of thing, because obviously that's wrong. And then propan 1-ol, 3 carbons. The OH is in carbon number 1. Again, you could put it here, or you could even do it on this side. And then surround it with hydrogens. Like so. Name another alcohol which is the same molecular formula as propan 1-ol. Well, we just move this OH group to here and move the hydrogen to there. We would turn it into propan 2-ol. Here's another question about fermentation. We have to describe the process, including the starting materials used, the conditions, and any other products. Part 1, name the reagent used to convert propan 1-ol to propanoic acid. So how do we convert an alcohol to a carboxylic acid? This is where we use acidified potassium dichromate. What colour change is observed? Again, this question has been asked before, and it's orange to green. The type of reaction, alcohols get oxidized into carboxylic acids. So that's oxidation. Part 4, a balanced similar equation for the reaction of propanoic acid with magnesium. Okay, so propanoic acid has got 3 carbons. So it's going to be Mg plus C2H5COOH. You'll find propanoate on the back of the data leaflet. And propanoate is C2H5COO. And there's a minus there, so this has a valency of 1. The magnesium has a valency of 2. So when we swap, we end up with this. And there's a metal plus an acid, so we get our salt plus hydrogen. And then to balance it, we've got 2 here, so we need to put a 2 here. Again, this magnesium could be on this side, but it's typical to write it like this. Part 5, what's observed when the propanoic acid reacts with magnesium? So things like the metal disappears, colour solution formed, fizzing, or heat released. Okay, so name the process used to separate crude oil into its components. Well, that's fractional distillation. And remember, the different liquids in crude oil have different boiling points, so when they're heated, they can be separated. And you've got things like refinery gas and naphtha up towards the top. And then as you go down, the longer chain molecules have higher boiling points, and so you get diesel oils and so on. Hydrocarbon we've done before. Homologous series, again we've done that. General formula for alkanes is CnH2n plus 2. Okay, so on to C part 1. Now this is about cracking. Now cracking is the breakdown of a long chain saturated hydrocarbon into a smaller, more useful one, and an alkene. So you'll see what that means in this example. Now both sides of the equation have to balance. On the left hand side there are a total of 14 carbons, so that means on the right hand side there must be a total of 14 carbons. So this has got to be C2. Again, the hydrogens have to balance. We've got 30 on the left, there must be 30 on the right. We've already got 26, so that means there must be 4 hydrogens. That's it now balanced, and you can see that this is our long chain hydrocarbon molecule. It's now broken down into a smaller hydrocarbon chain and an alkene. On to 2, a reaction profile for endothermic. So I'm just going to underline that. This is an endothermic process for cracking. Label the axes and the activation energy. Okay, well, in an endothermic reaction, the products have higher energy than the reactants. So I've written in the chemicals that I start with and what I finish with, the reactants and products. And then I'm going to label the axes. Y-axis is the energy, and the x-axis is progress of reaction. So I've done that. I have to label the activation energy. Now the reaction pathway goes from reactants to products, and the activation energy will always go from the reactants to the peak of the hump, which is there. And make sure the arrow is going up to the hump. Okay, don't stop it here and put the arrow on. That's too far from this peak, if you like. So I'm just making sure it goes all the way up, and then it does say to label it. So EA would be fine, or I'm just going to write in activation energy. And what does activation energy mean? It's the minimum energy required to start a reaction. On to this calculation question. So here, what we have to do is calculate a value for the bond energy of one of the carbon-carbon bonds. Now, energy change equals bonds broken minus bonds made. So that's the first thing you've got to remember. Now, the energy change for this reaction is minus 2050. And then I've got to work out what the energy is for the breaking of the bonds and what the energy is for the making of the bonds. So let's do the bonds broken first. So the left-hand side is where bonds are going to be broken. Remember, this is an endothermic process. We've got 1, 2 carbon-carbon bonds being broken. And then count the number of carbon-hydrogen bonds. There's 1, 2, 3, 4, 5, 6, 7, 8 of those. So plus 8. Now you obviously don't have to write this out when you're doing the calculation. I'm doing this so that you can see where all the different values are coming from. And then we've got to add on the oxygen double bond, and with 5 of those. So now the values can be substituted in. Now I don't know what the carbon-carbon bond is. That's what I'm trying to find out. So it stays like that. And then that's going to be plus 8 times 412 plus 5 times 496. So what does that equal? Let's see, that's still that plus 5776. Now I'll work out the energy that's released when the bonds are made. So there are carbon-oxygen double bonds, but for each molecule there are 2 of them. And there are 3 molecules, so in total that would actually be 6 carbon-oxygen bonds. So it's going to be 6 C double bond O plus OH. Now there are 2 OH bonds per molecule. So that's 2, and then we're going to multiply it by 4. That's going to be 8 OH bonds are made. Now we can put in the actual values. So it's going to be 6 times 803 plus 8 times 463. So that gives me a total of 8522. Now, I'm going to make use of this energy change because minus 2050 equals, and then that's going to be bonds broken minus bonds made. So it's going to be 2 plus 5776 minus 8522. Now we rearrange the equation. So just move this up a bit. We're going to have to go underneath. Here we don't have enough room. So 2 carbon-carbon bonds equals minus 2050. I'm just moving these across. That's going to be minus 5776 plus 8522, which equals 696. Now remember, this is for 2 carbon-carbon bonds. So for the final answer, I've got to divide this by 2. So the carbon-carbon single bond would be 348, and that is the answer. E part 1, I'll have to give the values of x, y, and z. Well, x relates to the carbons. So let's see, there are 1, 2, 3 carbons there. So x is going to be 3. Y relates to the hydrogens. Let's see, so we've got 1, 2, 3, 4, 5, 6. And then Z belongs to the oxygens. So count the total number of oxygens. There are 1, 2, 3. Part 2, draw a circle around the carboxylic acid functional group. Well, the carboxylic acid functional group is the COOH. There's going to be that one. What do we mean by weak acid? So I've had that one before. That means it's partially ionized in solution or in water. Part 4, we've got solid copper 2 carbonate is added to lactic acid. 3 observations. This is just like copper 2 carbonate being added to any acid. So carbonates added to acids fizz. So that's definitely going to be an observation. Carbonates disappear when added to acids. You could say there that the green carbonate disappears because copper 2 carbonate is green. So I'll just put that up there as well. So you could have said that. That would have been an option. Now, copper compounds in solution are not colourless. So this is not like group 1 or 2 compounds in solution. Copper compounds are usually blue, or they usually form blue solutions. So in this case, you would get a blue solution formed. Sometimes heat released isn't awarded for this type of thing. The heat released is really small because we're using a weak acid. So it may be awarded, it may not. If you have put it, it will not be marked wrong. But I'm just going to stick with these 3 or 4 options here. Propan-1-ol, well, the prop tells us there are 3 carbons. The ol tells us it's an OH group on carbon number 1. And then oxidizing an alcohol to a carboxylic acid, so that is acidified, for 1 mark, potassium dichromate, and that would be the second mark. So name the carboxylic acid formed when propan-1-ol undergoes oxidation. Well, it's going to be oxidized to the corresponding carboxylic acid. It's going to be named after prop, and it will be propanoic acid. And then what is meant by the term polymer? That's a long chain molecule made from small molecules. Part 2, name this polymer. Well, polymers always have that structure. It's always based on 2 carbons. Now, all of the other atoms are hydrogens, which you can see here. So that means that this is named after ethene. So this polymer would be polyethene, or you could say just polythene. So draw the structure of the monomer from which this is made. So what we do is take this repeating unit and we remove the bonds either side, and then we put a double bond in between the carbons. And what we end up with is our ethene monomer. So I'm going to fill in this table. So we'll look at A first of all. It's an alkene. Have to write in the number of carbon atoms. Well, you simply count the number of carbon atoms here, and you should be able to see there are 4. The name of this is going to be named after an alkene because there's a carbon-carbon double bond. Because there are 4 carbons, this is going to be bute. Now you've got to say the number of the carbon to which the double bond is attached. So you can see here it's 1, 2. It actually doesn't matter, you can start from this end, 1, 2. So the double bond here, so in carbon number 2, so it's going to be bute hyphen 2 hyphen ene. The molecular formula, C4H8. On to B. We've got propan-2-ol. Well, the ol is the clue for the homologous series. It belongs to the alcohols. 3 carbons. The structural formula will therefore be 1, 2, 3. Now, the OH group, which is what the OL indicates, is in carbon number 2. So I'm going to draw that down. Be careful here that the bond is going to the O. Don't be writing it like this if I do it over here. Okay, so that's wrong because it looks as though this bond is going to the H. And then surround the rest of the molecule with hydrogens. The molecular formula is going to be C3H7OH. Alcohols are usually written like that with the OH at the end, but you could just put all the carbons, hydrogens and oxygens together. So what I mean by that is that it would be C3H8O. On to C, butane. The ANE tells us that that belongs to the alkane homologous series. Number of carbons, you just count them up, there are 4, and the molecular formula is going to be C4H10. Lastly, on to D, carboxylic acid with 1 carbon. I'm going to draw it first and then do the name and the molecular formula. The carboxylic acids have the C double bond O, OH, and then it's completed by putting in a hydrogen. So the name of this is methanoic acid. And the molecular formula is HCOOH. Again, carboxylic acids are usually written like this, COOH, but you could do H2CO2. On to part 2. So which of the compounds would react with acidified potassium dichromate? So this substance reacts with alcohols. It oxidizes alcohols to carboxylic acids. Well, the only alcohol here is B. So it's going to be propan-2-ol. And the colour change is orange, which is what the potassium dichromate is, and it goes green. Right, a balanced simple equation for the complete combustion of A. So C4H8. Complete combustion is going to react with oxygen to form carbon dioxide and water. And when balancing these combustion reactions of hydrocarbons or alcohols, start off with the carbons. So we've got 4 on the left. That means we need 4 carbon dioxides on the right. Then do the hydrogens. You can see there are 8 on the left. We need 8 on the right. So put a 4 there. And then finish off with the oxygens. So 2 4s are 8. Plus 4, that's 12. We need to make this 12. Name the reagent required to convert A into C. That means we're going from an alkene to an alkane. Well, if you look at this, you can see that hydrogen has been added onto it, which is the answer. And that's how you turn alkenes into alkanes. Weak acid, we've done that before. That means that it partially ionizes in solution or partially ionizes in water. State the type of polymerization which A can undergo. Well, alkenes undergo addition polymerization. C, let's move this up. Cracking question. A long chain molecule is broken up into a short chain hydrocarbon molecule and an alkene. Both sides of the equation have to balance. There are 4 carbons on the left. So there has to be a total of 4 carbons on the right. Already have 2. That means there are another 2. And this molecule is going to be a saturated molecule. So remember, cracking is where that long chain hydrocarbon molecule is broken into a shorter chain saturated molecule and an alkene. We already have the alkene here. So that means this one has to be an alkane, a saturated molecule. And then the hydrogens, well, they've got 3, 5, 7, 10. I already have 4. That means there must be 6 hydrogens left to fit in. And they all fit around this. So that is ethane. And lastly, how would you test for the presence of the unsaturated product, which is this one? An unsaturated product contains at least 1 carbon-carbon double bond. Well, you would add bromine water. And the bromine water will go from orange to colourless.